Yes, good morning, everyone. Our topics for today are we're going to talk, just to make you aware, we are not going to make any exercise, but also that in the same way that we have surface networks, we also have downhole networks inside a given wellbore. So we are going to have some small discussion, just very descriptive. So you have maybe you will have an exercise, maybe not, but I will think about it. But it's the same way that we solve surface networks. Then you have to apply the same philosophy to solve it for inside the wellbore. And then we're going to go to the side on the multiphase flow. Really, we have been dealing with gas or with liquid, but what you have in most cases is a mixture that is circulating through the tubing. And there are some other courses that some of you that took production wells, there is another course also in the energy department. So I don't want to dwell too much on that, but just to give you an idea how you perform the calculations, that you have to make them stepwise. And then just to prepare, we're going to have on Thursday a session in the lab, okay, where we're going to work with MBAL, Prosper, and GAP, which are kind of commercial tools to do the things that we have been doing here with Excel and that you probably encounter in your professional life. So that's just to prepare to things, nomenclature, things that we will see in that software. So that's going to be on Thursday. That will be the 9th. Okay, so next class, the 9th of March 2017, will be in room P2, the computer lab, just here in the ground floor, and you enter, there is a door diagonal to P1. Yep. And the topic will be, we will have a short session on MBAL, okay, Prosper and GAP. These are all commercial tools from a company called Petex, Petroleum Experts. And that will be the equivalent to material balance. That will be equivalent to flow equilibrium in single well. And that will be an equivalent for networks. Okay, what we use in networks. And actually, we are very lucky. We have a academic license, but we have only 10 of them, so you will have to work in groups, maybe 2 people. Yes. Okay. So any of you has any question about the exercise that you just delivered yesterday? Was there any big thing unclear? I think not. You have been asking, questions, and you have been communicating with me, with this assistants. So I hope there were not many holes left. But I will see in the correction. But what is that? 10? Yeah, 10 licenses we have. So you saw with networks that we have to solve against flow equilibrium is much more challenging because you have many branches, and if you have many junctions, if you have a very complex network, okay, and you have groups of wells, these networks, they might be in the order of from maybe just a few wells, maybe 4, it can go all the way to 600, 1,000 wells, okay, and then it becomes very, very complex. This process of solving networks becomes very time consuming. But no matter how you solve it, there are many ways to solve it. It's just a system of equations that you have to solve at the end. Okay, you have equations for each section, and so far we have neglected the bit temperature, but some cases the change in temperature is also important. So you have to include that temperature in the equation. Like the temperature seen from this side should be equal to the temperature seen from the other side, which make things more complex. But all the time you have to be aware that pressure calculated counter current and co-current is the same, okay, for a given point. If not, you have a control element, might be a choke, might be a pump that is going to breach. But all the time you have to be, if you have nothing in between, the two pressures have to be the same. That's one thing. And if you have many junctions, that means that the pressure has to be the same in all junctions. And then the next one, the next thing that you want, if that is if you're solving it in Excel or if you're solving it in one of these software, that you have to have a mass balance, okay? And mass balance means that the rates, surface rates, should be conserved. Okay, there is no magical disappearance and appearance of mass. You just all the time has to be conserved. That is to say that if I have a rate coming to this junction, the sum of all of these rates should be equal to the rate coming out. And you say equal, of course there is going to be all the time a small imbalance, okay, because there is some tolerance, we have some iterative process that we solve, and there is going to be all the time some imbalance, but this imbalance should be small enough that I can say, yes, these rates are conserved. Okay, that's the two things that you have to worry about when you do it in Excel, when you do it in any software. Yeah. Yes, so we have also, and you saw that the main problem with networks is that we cannot do just a standalone analysis. And you will see with subsea systems, it's going to become more and more common in the future. So all the time in subsea systems, we have this arrangement of wells, okay, of a commingling system that takes it all the way to the platform, all the way to where you have your facilities. So it's going to be important for you to capture this interdependency between the elements on the system. If I make any change in this well, you might think, well, it's 10 kilometers away, it's not going to make much, it's going to have some impact. And if it's important, not important, you have to run the simulation to see that if it's important or not. If you have a control element, remember you can fix the rate, and you can fix the rate, but then you have to find what is the delta P that you need to breach, to breach the pressure. So we also have downhole networks, and some examples are, some natural examples are multilateral wells. Okay. Multilateral, I have a nice picture to show it. That we, for some reason, we want to use the same wellbore, okay, maybe to save to avoid drilling, because here we will need to reach all of these areas, all of these parts of the formation. We will need 1, 2, 3, 4, and 5. So what I do is from the same wellbore, I sidetrack, and I try to reach from the same, I try to reach different parts. That's what I call a multilateral. And really, at the end, all of this branching adds a lot of complexity to the completion process. It's not so trivial to make it, that it will work, to make the branching, to connect each section to the same wellbore is not so easy. But there is a compromise between complexity on single well or the cost of too many wells to reach the same formation. Yeah, so that's one case. The other case that we have is if we have, for example, multi-layer wells, multilateral or multi-layer. Okay. Here you see each one of these wells. It appears that they are in the same reservoir, although in principle they could be in any other reservoir. Okay, they could be in another formation, but in this case it looks like they are in the same. I'm just trying to reach different aerial parts of the wellbore. But multi-layer, here I'm departing from the fact that actually I have different depth. Okay, at different depth I have different formations, and they might have different characteristics even. So here I might have certain permeability and certain, for example, reservoir pressure, 1, 1. Here I might have 2, PR2, and KR3, K3, PR3. But I chose to produce from the same wellbore. Now, you have a downhole network when, in this case, all of them are producing through the same wellbore. Yeah? Because you might have that, for example, in this case, you might have, let me make it a bit nicer. So you have one tubing, and you have a packer. Yeah, and that is producing from that formation. Okay, but then later you have another formation deeper. Okay, and then what I do, I just have a hole in the packer, well, or a passage through the packer, and I put another tubing. Okay, and I put a packer on that tubing. Yep. So it's like dual, they call it dual tubing completions. Okay, or dual string completions. But when you reach to the surface, each one of these pipes is going to have their own master valve, their own wing valve, but it's just in the same wellbore you put two tubings. But in this case, you can control all of them, the two of them separately, right? I can just choke. If I want to produce less from that, I choke, but it will be like having two wells in the same wellbore. That's not a network, okay? That's just two wells in the same, almost spatially in the same place. And if I have it in a, you know, if I'm going to make a sketch, I can almost have, like if they were two separate conduits, yeah? I can model it like that, like two separate conduits. While in this case, you see that the three of them reach to the same place. And that creates some problems. Like I told you, you know, when we have a network, it might be that that well is very strong, okay? That well is in a high reservoir pressure or either has a high productivity index, and the well next to it might be very weak, yeah? Might be have a low reservoir pressure, a low productivity index, and then you have the play that will try to produce more and that will produce less. Like this joke that you cannot have everything in nature, so probably if you are producing from there, you have a very high pressure, okay, but you have low productivity. So it's a well that has, it's a formation that has high amounts of gas stored or high amounts of oil stored, but it can produce very less, yeah. But then you have some other formation that has a very low reservoir pressure but has a nice productivity, so it's going to get depleted quite quickly. Also, something else that we have to account for here is that when we close the well, okay, if the pressures they are different, you are going to have cross flow. If, so let's say if PRI are different, one might have cross flow between formations. Okay, and some formations will start to charge. Okay, some formations, for example, that formation, if the reservoir pressure is higher than that one, it will start to charge the other one. So you will have some influx of one of the fluids to the other. One formation, high pressure for formations, high charge, okay, other formations. But we have to leave, if we are going to make that arrangement, here we can, you know, here we can play with the choke, okay? If we have, for example, one strong well next to a weak well, we can try to choke the strong well so the weak well can produce. Yeah. But here, if we don't have any control method, we are kind of on our own. Okay, we have to produce what nature give us. Okay, we have almost no control. And in relation with that, there are some things that we can make to control. So we have some, let's call it, we have a, with that idea in mind, that we say the things can be very different. Okay, that branch can be very different to that branch, can be very different to all of these formations. We can use something called inflow control devices, okay, ICDs, that they allow to control, that is to control, okay, and to control in a passive way, passive or active, the rates coming out of a given section, of a given formation, or of a given section. Okay, in that case, for example, in the case here, all of them are producing from the same formation, but they are different sections in the reservoir. Okay, they are different parts of the reservoir. Yeah, in this case you have different formations. But one typical example that we use inflow control devices for are coning wells. Okay, for example, in coning wells, coning horizontal wells, so let's say that you have, maybe we can make it, okay, we can make our wellbore. Okay, and that wellbore, let's say we're producing from an oil layer. Oil we depict it with green. Okay, and we have, just like that might be the case of Troll, or the case of this Uruku field that I showed you before, you have a gas cap, you have a gas layer, you have a oil, very thin oil layer, and then you have a water layer. The thing is that you might have some, if you plot along the wellbore, if you plot the permeability, okay, and in that case will be the horizontal permeability along X, you might have variations. Okay, you might have some heterogeneity along the wellbore. So that means that if you have very high at this point, maybe the water will tend to cone, okay, to the wellbore, because let's say that's kind of the resistance. Okay, the permeability gives you the resistance, is the proportionality between delta P, delta X, and K. Okay, it's a proportional factor. So if this one is, sorry, is the inverse, right? How is Darcy law? K dP dr over me equal to Q, right? So it's the inverse. So if the permeability is high, the delta P will be less, right? So it will have preferential coning, and you might cause some coning in these areas. Also, another reason is because if you see just the pipe part, just like a conduit, okay, that's in the formation. Let's put here, that's in the formation. And then you make, for example, the pressure. This is pressure in the wellbore. Okay, I'm just having a line, and fluid is flowing from the toe. That's called the toe, okay, and that's called the heel, okay, of the wellbore. So when the fluid is flowing on that direction, you remember if it's horizontal pipe and it flows from right to left, how the pressure should look like. Okay, it should look higher here. To have flow, you have to have higher pressure and low pressure at the end, right? Yeah. So again, if I have here the same reservoir pressure, okay, no, let me make some space. If I assume that I have the same reservoir pressure, okay, along the wellbore, then the driving force of the rate is going to be P minus this P, right? In each position inside the wellbore, that pressure difference. And you see that initially, that pressure difference, if we put reservoir pressure on this diagram again, I hope I don't make a mess. That's supposed to be an I. Sorry. I guess you should be used by now to my handwriting, but okay, so you have PR someplace here. PR, constant, very high. So initially, the drawdown, that's what we call the drawdown, right? Is going to be very small, so you don't do the rate here should be very small. But when you reach all the way to the end, the rate, the drawdown becomes very big. That means that you will have a higher rate. That means that you will increase also the risk of coning in that region, exactly at the heel. So that causes, so this causes, let's say here, this causes an uneven distribution of inflow, okay, of reservoir rates, along the wellbore. Okay. That means that here will be higher the Q, and then here will be very small Q. Okay, you start to deplete, so that will be Q at different positions. Okay, so Q will have also a distribution like that, and that causes, which in turn can cause coning, which can cause coning, uneven depletion, etc. Okay, but basically you can have early breakthrough on the heel or on areas where you have high permeability, on streaks where you have high permeability. And if this wellbore is, for example, and you say, okay, but why might be so big change? Okay, if this might be a few hundred meters, but in some fields it might be all the way to, I think the current record is like 6 kilometers. Okay, so actually it might be very, very long, that wellbore, and you might have important variations of permeability along it. So the way, the solution we make is, that we try to make is if we have our wellbore, okay, and let's say that we have open hole completion, that means that so here we have our production casing, reaches all the way to here, and then we have an open hole. Okay, that means that we just make the hole without doing anything else. Then we run an inner section of pipe, okay, and of course we make a packer. We put a packer to be sure that the fluid is going to come through the pipe. Okay, that pipe has some isolation packers. Okay, to divide the wellbore in sections. So I divide exactly that part, and that part. I divide the wellbore in sections, and might be sections of from 50 to maybe 200 meters, okay, in a wellbore of 1 kilometer or 2. And what I do next, if I put, now I have to communicate, right? If the fluid wants to come from the formation and inside the tubing, I have to make a hole. But then what I make, I say, if I expect here the drawdown, okay, now I have PR and I have PWF, okay, that is the biggest in the heel, the difference. And here, PR, PWF, that will be the smallest. So what I'm going to make a hole, a big hole here. I'm going to make a very small hole here. right? So it's like I'm helping nature in a way. I say that guy is privileged, okay? That guy has a very big delta P. So I'm going to make some kind of small handicap. I'm going to put a very small hole that will create, this small hole will create high delta pressure, okay? And then I put the two of them in the same level, okay? If like you have a high performance athlete and then you have myself, or you have maybe one of you is a high performance athlete, and then you give the big the high performance athlete, you give him some drinks, or you give him something to make him, you know, go slower, and then we can go at the same pace. So that's exactly what we are doing here. Yeah, the idea is okay. So here, if you see, we create, by doing that, we create a network. We can, if we were going to put that in terms of pipeline, okay, if we say, so that we will have one section up to here. So let's call that P at the heel. Then you will have PWF1. And then we say from the formation comes, here we have one box that will be, that is what we call the ICD, okay, the inflow control device. In our case, I told you, just an orifice, just an orifice of certain size. And then we have another box that represents the IPR, okay, the pressure drop in the formation. And then finally we end up with reservoir pressure. And then we go to the next section, the next PWF, okay. Then we have another ICD that will have another opening too. If you want to learn it, how to design it, you have to take these production wells course. And then we have PR, IPR, okay. And we progress further. So this will be, that section will be flowing pipes. So we need an equation for flowing pipes. That equation will be flow in an orifice, and then that equation will be just an IPR. And so forth. Pipe, IPR, orifice, and IPR. Pipe, orifice, and you can have actually a very big network. Okay, with many things there. And of course, here I haven't told you the full truth, but then this hole, I cannot make it exposed directly to the open hole, because here I might have crumbling problems, right? That here, that wall might crumble, and you might have plugging. All of these sand might damage and cover my hole. So I need also some, sometimes I use a slotted liner, or I use a mesh. Okay, I try to make, and we will see just one wire mesh. Okay, but the point is that I have to define, so in design of ICDs, I have to define the number of sections. That's the first thing, how many sections I want to make. Yeah. And how many sections I make, I say, when is the pressure drop significant enough from one point to the other? Okay, let's say 20% pressure drop, so I put each one of them every 20%. And then the next thing is to define the orifice diameter and the number of orifices. Because usually I don't have just one, because if I put one, that will be a huge pressure drop. So I put a bunch of them of the same size in the same section. That clear? So in that case, I create this network that I have to solve. Some commercial tools to do that are, maybe some of you will use it in your professional life, net tool. Okay, that's from, I think it's Weatherford. Okay, but just check. But I think I'm almost sure it's Weatherford. Where you can, that's called kind of completion design. This this goes inside another course that we don't teach, unfortunately, here at the department, but that's completion design. So what happens if we go now back to that case? Okay, how do we control what comes from each formation? Okay, let's say that the formations, they are very different from each other, and if we don't put anything, these two formations will never produce, and that will be the one producing all the time. So how do we control or give this handicap to this one and promote the other two? Okay, so we can do exactly the same thing. Okay, we have one single production pipe, production tubing. We have the first formation. We can make it maybe with two here. And we have another packer and the second formation. Okay, so what I make is I make again some kind of device, some holes that they will have a smaller size here and, for example, a bigger size here. Okay, such that that formation will have a handicap. We have a delta P. At the end, the delta P that is C is equal to that delta P, so they are producing depleting at the same rate. Because what might happen if, for example, you are producing these two, might be that, let's say we said that that's a low pressure, okay, low N, okay, the initial oil in place and high permeability, and this is high pressure, high N, and low permeability. That will take a long time to deplete because it has a huge size, it has a huge pressure, but then it's producing very little, right? But this one will produce very quickly because the pressure is low, the N is low, but it can produce, it can give. So there will come a point, maybe you had planned to produce that for 20 years, and after 10 years that is already depleted. So it's not giving you much to the production. And it might be stealing, okay, that when you close the well, it's stealing and charging fluids, and you still have to produce them out. So for that case, I do the same. I put a control element, okay, and sometimes they are depicted like that. I will show you right away a picture, okay, and I call it just a control device, downhole control device. Let's see. Okay, so that's the picture I told you about, pressure drop, and here you have a nice schematic. So let's put that. I think that's from an SPE paper. You see, very nice hand sketch. So you have your packer at the top, isolating the production tubing with the casing, with the section, and then you have other packer. Usually these packers, they are, if you have an open hole, okay, these are swellable packers that you almost inflate. It's like a balloon, okay? You inflate, and because they have to have high deformation. This packer has a very low deformation. It needs that this distance will be very, very small from the beginning, okay? Because it has a very small deformation. But these packers, because you cannot control exactly what the size of the open hole will be, these are high deformation packer, okay, or also they call swellable packer, or inflatable packer, okay. And this is just a common packer because there you have the two parts made of steel, and you can control exactly what will be the space between them. So that's kind of a regular production packer, okay. And you see that the fluid kind of enters. You see this thing that is kind of lined. This is the mesh that I was telling you about, okay, that protects all the sand, traps all the sand in the upper part, and then it circulates along this small area, and here is where you have the opening that comes in. You can have different designs, but I think I have a nice picture someplace. Okay, so that's how it looks like in 3D. Okay, it enters through a mesh, okay, through some place that avoids the passing of sand, then goes on the annular space. You have some orifice here, and then you have the main orifice on the when it goes inside the tube. And what you regulate is the opening of this orifice in each section. And you have also another design. I'm just going to put it here just so you know, but you also have this helical channel that instead of using these orifices here that the flow goes actually, now the flow has to travel in some kind of it's called helical way. Okay, it has to go helically along the tubing. That produces more pressure drop, and it's equivalent to this flow in these openings, and until you reach the same holes and you go inside the production tubing. Okay, that clear? Yep. So let's so now there is one more thing I want to mention about this topic before we close it, and is that so far we have discussed passive. Okay, passive, that means that the hole, we cannot change the size of this hole. Okay, it's all the time going to remain the same size, but that means that with depletion maybe that hole is too big, okay, and I have no way to control it. So let's so far we have discussed passive, okay, because they will remain the same way along the life of the field. Passive inflow control devices. But we also have active inflow control devices, okay, and they are usually called ICV, okay, inflow control valve. Okay, and we have two types. There are two main types now. One of them is that it's like manually activated. Okay. Or I have something called autonomous. That they regulate automatically. And I don't want to go too much there, but manually activated, let's take a picture maybe to save time. Okay, I have, if I want to activate manually, okay, you have to want to have an operator in the surface controlling what will be the opening. Okay, you have to have a hydraulic line. Okay, all of these things are controlled by pistons. Okay, so let me just try to make a sketch. If we have the wall, okay, let's try to make. Okay, so we have the main wall. Okay, and we have an opening. Okay. And then we have inside an element that has a lot of openings, then has a part that has only two, and then has a part that has only one. Okay. So let's see. So this will be the high Q opening. This will be the medium Q opening, and this will be the low Q opening. Okay? And then we can just have the same thing symmetric, okay? Because that's the outer. Here you have, this is the annular space, and here you have the formation. Let's say that you are perforating, okay? Here I'm making kind of a cut, okay? I'm just looking at the pipe. If the pipe is like this, I'm just making a cut through the middle, okay? And I'm looking at the plane that comes up, right? That clear? Yep. So here the fluid is coming in, and the first thing that it encounters, and that will be the closed part. Okay? So if I don't want to produce anything from that well, I just pull it up, okay? And then it will be closed. If I want to produce a little bit from that well, then I expose the low Q opening. Then if I want to produce more from that well, I expose the medium. And then if I want to produce even more, I expose the high rate. And actually here we made a small mistake. We have to make the opening bigger, so it will expose all. Here I also made a mess. Okay. Small mess, not big. Yes, that clear. How do we control? Yeah, we are changing, in a way it's like changing. We have a fixed opening, we have multiple openings, but I have different options, and I have to place them in front of the main opening, and that's how I'm able to control. Okay, so now the question comes, how do I activate that? Okay, I need a piston. Okay, so I need, this line has to carry, okay, okay, to move it up and down, I have to have something like this. Okay, let's make it a small opening here. Okay, so that line comes here, and if I want to move it down, I just pump it, push it, and it will move it all the way down. Okay, if I want to, it will go the other way. I can do the same arrangement here. That's not exactly how it is, okay, but just to give you like a schematic description. Okay, you push it on that side, and you come with fluid and you push it on the other side, so it goes up and down, up and down. Yeah, but you need to have these lines that they have to carry some hydraulic fluid. Okay, that clear? Yeah, and also I need some other things, like I need to know which section I have, okay, because I cannot be blindly, if I go down, how do I know which one is in front? Is it this one or this one or this one? So one thing that is also done is that I put some magnet, okay, I put here a receptor, an electric receptor, and here I put a magnet. So that will be a magnet, okay, and that will be a receptor. Okay, and this receptor can tell me, and it will have magnets all around the tool. Okay, so this goes with a line to the top, another line. Okay, here you see I need one hydraulic line going from the top down, and I need also a line coming, of course, with the energy down and then up, so I need two. Okay, and that will tell me where I am. Okay, that will tell me the location of my tool. Okay, we have one. I will see if we can go maybe next week to see it in the. We have one tool that you can watch. It's real size. Okay, it's almost as long as this room, and it has all parts. It has actually it has that part, and it has this part with the packer and everything. Okay, so you can see how it looks like, but that I'm telling you how it works. Okay, what it has inside. So maybe we will try to go next week to the workshop you know, they think it's ugly, so they keep it in one place there hidden, and they hope to throw it away one day. But it's so nice that you have real size. You see, here we're talking on paper, maybe we imagine this size, but really it's a huge thing. Yes, so that's how I control, and I can know exactly what opening depending on what is the drawdown, which section I'm depleting. You can control how much comes from each formation. But I create a network, and I create another. It's like a downhole choke, okay? Downhole adjustable choke. Okay, that I have another variable to play with on top of the wellhead choke. Now I want to make a short comment on autonomous, but do you think we take a break first? So you can stretch a bit your legs? Yeah, 15 minutes? Okay, let's, so that's a video that is on my YouTube channel. And that's the equipment we have at the lab. So you see, that part that is in red was cut. Actually, that should be completely covered, just like here, but that's just to show you what is inside. And yeah. So you see, that's the holes that I told you. That's the part that has more holes, more density of holes, and is very much below. And you see above, you have that part that is exposed, where you present the holes in front of that part, and that's the part where the fluid from the formation goes inside. Okay, you continue that part. Here, this block is the block where you have the hydraulic connector. You see the pipes coming from the surface all the way 2 kilometers, 5 kilometers down. And then you have this part. I'm not sure if it's visible here, but you, yeah, that part, let's see back. We make it a bit bigger. Very poor quality, but someplace here on that is the magnetic strip that used to locate to see where it is, but it's actually quite big equipment. It's real size. Here you have again the hydraulic lines for each section. Okay. Huge tool that we have here, and I hope to take you to see it another day. Okay, then let's talk very briefly, because we have to go to our topic today, that is multiphase flow, but let's talk about autonomous. So remember, when we have passive, very simple, we just leave it there, and the same orifice size with, if we want to change it, we have to make a major well intervention. We have to, take out the Christmas tree, put a BOP, bring a drilling rig, and make a big change in the completion. Not something that we want to make. We want that equipment to last for the whole life of the well. If we want to make changes, we need something like that, but we need a bunch of things. We need something to tell me where it is, in which position I am. That is electrical lines, and also need some hydraulic lines to move the equipment up and down. Then autonomous is kind of a technology that is coming out, has already some time, maybe since 2010, that basically it's self-regulatory. Depending on which fluids you have, it will try to close or open. And so let's make a simple sketch. Okay, and I'm putting here the wall very, very big, but actually it's not, well, actually the tubing wall might be something like that. Okay, and the valve is protruding outside of the tubing wall. and actually the valve is threaded. Okay, so it's so there is a thread here, so you have a hole in the tubing. Okay, you have a hole in the tubing this size with a thread. Okay, and then you screw the valve on that hole. Okay, that clear? Yeah, if you see that from the side, it will be something like that. So we have a hole with thread inside, and then you just go and screw that part. That is the autonomous, they call it autonomous inflow control device, or also autonomous inflow control valve, all kind of names. But basically the idea is that if you have fluid, if you have oil circulating through the device, then here you have some support. Okay, you have some blocks that are supporting that valve. So if you have oil all the time, that's going to be pushing this disc against the blocks. But now if you have gas, for example, what might happen is that because of some strange effect, okay, this might go up. Okay, and actually it separates. Let me just take out these streamlines. Okay, with oil it's going to be supported, but with gas, okay, it's going to separate, and it's going to become closer, to get closer. No, not so close. Okay, a bit closer. It's going to separate, but it's going to become a bit closer to the upper wall when it has gas and when it has water. So if you see the opening, which is that distance between these two, okay, the opening changes H, let's call that H, changes depending on the fluid circulating. Okay, for example, if it's gas that has low density and low viscosity, it will closes, and if it's water with high density and low viscosity, it also closes. Okay, and only likes it opens, okay, and it won't close completely. Okay, it will still keep some space to circulate, but it opens when oil that has a medium and a high viscosity. Okay, just to exemplify that, I just brought some small experiment that you have. It's just a plate, okay, a disc, and then you have, that will be kind of the fluid is coming from the reservoir through that opening, and it's flowing in between, okay, these two plates and going out. Yeah, exactly the same thing we had in our drawing. Imagine that this part is this disc, okay, and that part is up here, right? So I just put a guide here so that when I blow, it won't move to the side, okay? But if you see, let's see what happens when I blow air. You see, it sticks to the top completely, okay, non-logical, okay, some kind of clinging effect. Yeah, so that's that effect. You also have it in the valves of the reciprocating pumps. It's called clinging effect, and that device uses something like that. It uses that effect, so that moving part sticks to the top, reducing the opening, thus choking the flow. Clinging effect. And you have all kind of crazy variations of the same technology, but it's something that is becoming more and more common, so you should at least be aware that it exists. How does it work? And basically it's self-regulatory. Depending on the fluid that it goes, it will close and open, or at least that's how it's supposed to work. Any question before we leave? I see. So the conclusion, let's see if I have some more nice images. I don't think so, but the conclusion is that you might have downhole networks depending on the completion. If you have multi-branch, multi-layer, multi-layer, if you have some also not only there, but if you have some big variation of properties along the wellbore, if there is a big variation of properties, and actually to be more specific, of reservoir properties along the wellbore. Okay, then in that case, for example, there is a big change in permeability. I just split into sections that I assume they have constant permeability. But we can have downhole networks. We solve them the same way. We assume a rate or we assume a pressure, and we try to converge that. In this case, I will have a bunch of junctions. Okay, so I have to make sure that in each junction I have mass conservation and I have pressure conservation. Okay, you probably will get an exercise to practice. Okay, so we close that part. It took more time than expected, but now we go to multiphase flow. And as I told you, the most common case is that we have multiphase flow in the wellbore. Okay, we have multiphase flow in the tubing. And why is that? If you see, let's say we take, okay, our PT diagram, okay, and you remember something like that, and you had, let's maybe use some other nice colors. We had the bubble point line and we had the dew point. Those of you taking the course of Curtis right now, you know you are having an advantage. You have it very fresh in your memory. Dew point line and bubble point line. And then we have the critical point. And how do we call that maximum point here? That will be Crecondensitherm. So I'm not sure how do you write it. Crecondensitherm, like that. And you have Creconden bar. Okay, not pressure but bar. So the thing is that when the fluid, let's say that the fluid enters into the wellbore, okay, remember, let's say for example that's a gas cap, okay, you have oil, but the pressure at that point is the bubble point pressure, right? Bubble point pressure at that reservoir temperature. When I start flowing towards the wellbore, the pressure, if you plot the pressure versus the radius, okay, it's going to do something like this. Very sharp, very abruptly. Okay? That means that for all the remaining points close to the wellbore, you're going to have gas liberation. Okay? You're going to be in saturation. So you will have, for example, a bunch of the saturation of gas will be very high, and when you go away, it will be lower and lower and lower. So it might be, the point is that it might be that the fluid coming inside the well, okay, and to the tubing, if we put our tubing here, and I shouldn't be using this color. Okay. It might come already in two phases, okay, might come already saturated. That means that I might be already here, okay, with that composition, or it might be, let's say you're producing from an undersaturated, you have no gas cap, I might be coming from here, or if I'm producing just gas, I might be coming from here. Yeah, so that's the entry point, possible entry points. Let's put it here, possible entry points to the wellbore. Okay, but if no matter what I have, okay, the thing is that pressure and temperature are going to drop in the tubing. Pressure and temperature drop. Okay, so let's imagine that I came initially, so I go down and down and down, and that means that I will have, if you remember here, I have some ISO quality lines that they tell me how much gas I have, right? So this x equal 1, that means that I have mass of gas divided by total mass. Then x equals 0.95, etc. So that means that I have, yeah, let's say 0.6 or something, okay? So as I progress from the bottom hole all the way to the wellhead, okay, I will experience a reduction in pressure and temperature, and that means that gas liberates from the oil, okay? Or if I come from this point and I go inside, that means that oil liberates from the gas, right? Or comes out of solution. It's a better way to put it, okay? So if you see in, you know, maybe we have done this drawing before, but if you see on the tubing, if we make a zoom, okay, you have my packer and I have here my formation. If you see, initially I will have oil with some small droplets of gas, but then as more gas is available, is liberated, then these start to clump together, okay, and start making some clumps and some bubbles, okay, as I go up and upper and upper in the tubing. Then they start coalescing until they form some kind of what we call slug flow. So that we call, yeah, let's wait with that for a moment. So then you have some kind of plug structure. Then at the end, it might be, okay, it might be that you even have just all the oil is located in the walls and some part in the center, and then you have all the gas circulating in the center, okay, that until we reach the top. It might be that you don't have, depending, because it depends very much on where do you depart. If you depart, for example, here, and you're just entering here, you won't have, remember here we have one more that we are missing, maybe, that is homogeneous, just a single phase liquid. Well, you might have single phase bubble and maybe it stops there, but then if I continue reducing pressure and temperature along the tubing, you're going to have more and more and more liberation until you find all of these configurations of the flow. Okay, these are what we call flow patterns. Different ways how the fluids are spatially arranged, and we give them names. Okay, that in that case, this one here is called bubble flow. That one here is called churn flow. That one here is called slug flow, and this one here is called annular flow. Okay, I think I have a picture of and for gas the same thing. Okay, again I have pure gas, some mist flow, then that mist starts to stick on the walls, then at the end starts kind of almost blocking the pipe, and at the end I have just the same, this slug flow that I had before. Okay, so in gas that's called mist flow. Then I have some dense mist, Then I have some annular flow. Then I have some churn flow. And then I have some slug flow. You might have all of them depending on how the pressure, temperature, and how is your envelope. Okay, how is your phase diagram. Now, how do we deal with multi-phase flow? You have seen already that single phase. How do we deal with it? Just with this Bernoulli equation, right? And we calculate losses, hydrostatic and pressure losses. But how do we deal with multi-phase flow? By the way, any of you has taken any courses in multi-phase flow?
I'm taking one now.
Taking one now? What is the code?
Multiphase flow, isn't it?
TEP 4520 maybe, I think. With Ule.
No, I think the teacher has changed.
Yeah, he's on sabbatical now, but he's the one usually teaching it. Maybe now it's Siling Yang.
Yeah.
But I think it's this code. Just check it. Course on multi-phase flow. Okay, so there are different ways, okay, how we deal with this flow. With how do we, because the main idea is to calculate, be able to estimate delta P, right, and delta T with length. The thing is that something that you already have to have in your mind is that it won't be the same calculation method for all of these flow patterns. Okay, so we cannot use one unique method for the whole tubing. Okay, we have to split, so that's something that has to be clear due to the variation in pressure and temperature and the variation in flow patterns. The delta P calculations have to be made in a stepwise manner. Okay, I have to divide my tubing into segments that I assume they have more or less the same flow pattern, and then I have to calculate the delta P in each one of them in a stepwise. And we are going to have a small exercise here in class later. In a stepwise manner. Okay. And there are different ways. So, and also one more thing that you have to make is that there are two ways to study multi-phase flow. Okay, one way is the steady state, and that's what we use for everything. Okay, for all of our calculation, we say we want to avoid transients. Okay, we say that this term on all the equations is equal to 0. The derivative, partial derivative with respect to time, is 0. Okay, why? Because we say we progress from one steady state to another in the life of the field, so there is no need for that. But there is also one big thing that we won't have time to go in this course, that is the transient. So just to be sure, here we have all of our simulators: pipe sim, pipe phase, Rio, Prosper, and Gap, and all of these simulators, they are steady state. All of them neglect the transient part. Okay, but we have some issues that they are transient, like I explained before. Like if you have a transportation pipe, okay, that is, for example, is having some gas with some liquid, okay, the liquid might tend to accumulate in the lower part. Okay, with time it's going to change and accumulate, increase and increase until it blocks the pipe. When it blocks the pipe, that pressure starts to increase, okay, because it has a blockage. The pressure at this point, if you plot the pressure versus time, initially you had a constant, then starts increasing until it reaches one point that is able to flush, and it takes sweeps all the liquid to the next section. Okay, so this kind of phenomena, and that happens in so you have, for example, that's called liquid accumulation in gas transportation, pipelines, or you have also slugging, okay, or you have also slugging in risers. All of that is transient phenomena that we have to analyze using different tools that we actually don't use too much when we do field planning. Those tools are commercial tools, are for example Olga or LedaFlow. Okay, and when we want to look at transient, if we want to look at that term, particularly what is going to happen with certain things, for example how much liquid is going to accumulate, we need to use another tool. It's called transient multiphase flow simulator. And some people say that steady state really doesn't exist in multiphase. You always have transient, but it's an approximation, works okay so far, and it simplifies very much the equations and the way that you handle the results. Okay, in this case you will have to analyze, for example, pressure drop, the pressure at that particular point in time. Okay, and you have to run, for example, you will have to use a time step, for example, of every 0.1 seconds. And if you want to model the whole life of the field, how much does it give you? How many points, data points? A bunch, okay? If you do simulations and calculations of that pressure every 0.1 second, okay, and then you run it for the whole life of the field, that might be 30 years, okay, you're going to have a bunch of points. And that's really difficult to how to process all of these points, how to analyze all of these points. So people just say, we don't have transient, we don't have. But we will see in flow assurance, that's very important, and we will try to make some calculations with that. Okay, so there are, and now on the other thing, there are two approaches to study or to analyze multiphase flow. One of them is that we call correlation based. Let me search if I okay, so basically we have one approach that is correlation based. People try to make measurements in the lab. Okay, they put for example a pipe section. In this case, in the first focus was on the wellbore. Okay, what happens on the wellbore? So I know most wellbores were vertical or with some inclination. So they put a pressure gauge here, a pressure gauge here. They measure how much rate you had. Okay, you had a pump that gives you some liquid. You had a compressor that gives you some gas. Okay, and usually they were made with water and air, many of them. And you mix them, you send them to the main pipe. You are exactly computing how much you are circulating, and you report the flow pattern and the delta P, and we will see later something else. But then they develop a correlation based on those measurements. Okay. Then there is another approach, and that we have a bunch of methods. Okay, we have Bex and Brill, and we will see them. We have Orkiewski, we have Duns and Ross, we have Okay, all people trying to make more or less to improve the models, but basically they're very heavy based on correlations. They measure values in the laboratory and they develop correlations, but these correlations, of course, they are a bit limited in the sense that they depend on correlations developed based on experimental data. Okay, with some physics, but not much. Some physics, some models, some conservation, some physics, and with limited range of applicability. If you go outside, if one goes outside that range, it doesn't work. Okay? And one thing that was very clear from the beginning was that if you want very nice number to, it's like what you, if you think about the analog of the Moody friction factor, okay, that you have F and versus Reynolds, they found that that number, the Reynolds, which is some velocity scaled, okay, it's like the relationship between inertial and viscous forces, right? V rho divided by, okay, but it's kind of an adimensional velocity. They found that it behaves, it gives you a very nice correlation with, okay, with the friction, okay, with the pressure drop. Well, in this case, they found that a number called the superficial velocity, that is nothing more than V superficial velocity, Vs, and then we say of the liquid. Okay, initially they were studying just two phases, and they say that's Q of the liquid rate divided by the total area of the pipe. And that Q, I'm asking you now, what units does it have? Standard or local? Is it in standard cubic meter per day, or is it in cubic meter per day? It's in local, okay? When we, remember what I told you, when we describe pressure drop, the physical principle of conservation, we usually use local, okay? And then we have to convert to standard conditions. So we use that part. Okay, and actually we don't use it by days, but we use by second. And that's the cross-section area of the pipe. Okay, that is just pi r squared. And the velocity, superficial velocity of the gas, which is the Q of the gas divided by the total area. So if they make a plot of USL versus UG, or USG versus USL, they could identify that some particular combinations, they gave you bubble flow. Okay, that combination gives you, for example, stratified flow. That particular combination gave you annular flow. That particular combination gave you slug flow, okay, etc. Yeah, so that was the first observation, that every combination gives you exactly, but that depended on, this plot depends on fluid properties. That means density of the oil, density of the gas, viscosity of the oil, viscosity of the gas, surface tension between oil and gas, interfacial tension between oil and gas. What else? Depends also on the inclination, pipe diameter. Okay, so it's not very universal. Okay, it depends, and especially the transition between them. If you see, you jump from here to here, you will have a change in the flow pattern. Okay, that transition, depending on which system you have, which properties might be a bit more to the left or might be a bit more to the right. So let me just pull, I think I have, okay, like that. Okay, those are the early maps. That's from, it's called Mundane, I think. That's a flow map of Mannheim, and I think that was in the 50s someplace, but I'm not sure. Okay, so that application was working, okay, but was very restricted to the testing testing conditions. So then comes another option, another way that is called mechanistic modeling. And it consists on applying mass conservation for each phase and momentum conservation and momentum conservation usually might have two ways, okay? Might apply to each phase or you might apply to the mixture. And then on top of that, when I apply the two equations, we won't go in detail into that, but you will see that you have more equations than unknowns. Okay, so you need some additional things. So you need some closure laws that are derived empirically. Okay? That are derived by experiments. So they still need some experimental component, but by including the conservation laws, mass and momentum, they're able to be kind of to capture more what will happen if we change properties, we change inclination, we change diameter. Their applicability is is kind of enhanced, okay? And of course they need disclosure laws that they want to depend less and less and less on them, but really they still depend very much on experimental data. Okay, but just to use these closure laws to allow them to define some things, some unknowns, to make the system that you have the same number of equations and the same number of unknowns. See if I'm forgetting something. Yeah, those two are okay. So if you see it in a in a very simplified way, okay, if we are going to apply, that's the momentum equation of the mixture. Momentum equation of the mixture. Okay, I have that my pressure gradient depends on the one part that is due to friction, one part that is due to gravity, and one part that is due to acceleration. Okay, and if we now substitute how each term looks like, okay. Now we will go to some very first. You want to take a break? 15 minutes? Yeah. Or you prefer to finish early? Huh? Break? Okay. Take a break. Okay, so now before we go to the way how we calculate pressure drop in conduits, okay, this is not only for the tubing, but might also be applied for any flow line, pipeline, anything with multi-phase flow. But let's go to two very important definitions that we need. First, that you see, that's a momentum equation for the mixture. Okay, and it's exactly the same as single phase. The only difference is that now you're using a two-phase velocity, a two-phase density, and a two-phase friction factor, but it's exactly the same. So one thing so first, if you see any flow pattern, okay, for example in the pipe, you might have any distribution. For example, you might have bubble flow. Okay, if you cut the pipe, you have something like that. You might have stratified flow. You might have this annular flow that I told you about. But we don't focus about how it looks like. It's important to calculate the forces, okay? But one thing that we make is all of them, we say we group, we take all of them almost to stratified flow, okay? We take all the liquid to one side of the pipe and all the gas to the other side. So we try to make all of them liquid. And if we put it, maybe let's make a 3D figure. Okay, we group all the, doesn't matter how the flow pattern looks like, but I try to group them. Okay, into liquid, gas. Okay, and then each one of them will have a characteristic velocity. Velocity of the gas and velocity of the liquid. So if we assume that they are the same, okay, if we assume that Vg equal to VL, okay, then that's what we call homogeneous model, okay? Or we say no slip model, okay? Slip is where the two velocities are different, and that's actually the most frequent cases that we have slip. Flow patterns that don't have slip are, for example, bubble flow or mist flow. In that case, you can assume that the two phases, because they move in almost like a very agitated mixture, they move at the same speed. But that's not usually a good assumption for all the other flow patterns. So I'm going to ask you, how do we express that velocity? That velocity we can depart from, for example, if we have the mass flow of the gas and the mass flow of the liquid, right? That's something that comes in units of kilogram per second. Then we say we have the density of the gas and the density of the liquid at that particular point, at that particular pressure and temperature. And then we calculate Q, the local flow rate of liquid and gas, right? So this will be mg divided by rho g, and Q liquid will be m liquid divided by rho liquid. And then to calculate the velocity, we have to divide by this area, we will call it A liquid, and this area we will call it A gas, and we know that A liquid plus A gas has to be equal to the area of the pipe, right? Yeah. So then we divide even further, we say Qg, velocity of gas, and please don't mistake that by the superficial velocity. Superficial velocity is by AP. Okay, now we are dividing actually the area that is flowing through. That is area of the gas, and velocity of the liquid is Q of the liquid by area of the liquid. Now, if if homogeneous model, then we are saying that QG over AG equal to QL over AL, right? Now I'm going to make just some trick with the equations. I'm going to say that AL is equal to AP minus AG. Okay, I substitute that here, and I end up with QL over QG, AG equal to AP minus AG, right? Then I end up with QL, QG, AG plus AG, AP, and then I end up with AP divided by AG plus 1. Then I take the inverse of that and I obtain AG over AP, and that is kind of a very nice number. That tells me how much from the whole pipe section, how much is being occupied by the gas. Okay, which fraction is occupied by the gas. But remember, this is assuming homogeneous flow. 1 over QL over QG plus 1, and that gives me QG over QL plus QG. And you see something surprising, that if we say no slip, okay, we say that the two of them travel at the same velocity, V liquid and V gas, then the ratio between what the gas occupies to the total gas, to the total area, is equal to the ratio between the volume rates. Okay, that clear? So that means if you have homogeneous flow, you can calculate straightforward how much is occupied. So this is what we call the gas volume fraction. And this density of the mixture, even more, this density of the mixture will be, this we will also call lambda G. Okay, and the density of the mixture is this lambda G times rho G plus 1 minus the lambda G plus times the rho L. Okay, and I can calculate exactly in my equation before what will be the density of the mixture. I can calculate the velocity, both of them move at the same velocity, and I really can evaluate using the homogeneous model. That clear? Yeah. Now life is not so simple. Okay, we usually have U L is different than UG. Okay, they have a different magnitude. What will that cause on the cross section area? Okay, let's say that we have our case with no slip. Okay, it's like that. Area of the gas and area of the liquid, right? But now what happens, and the two of them travel at the same speed, VL and VG. But what happens now if the, sorry, nobody's correcting me, that should be BG and VL. What happens now if BG is much higher than VL? Okay, what happens in that case? Okay, we are still circulating QG and we are still circulating QL. Okay, that's still there. So that if you see that view, VL times AL equal to, sorry, again VG VL times AL. So if this one increases, that one has to decrease, right? And if this one decreases, that one has to increase. Okay, so at the end you end up with slip if the gas travels faster than liquid. You end up with, let's repeat that figure. Okay, you end up with, instead of this initial condition, you end up with this initial condition. Okay, here you have, sorry, that should be red actually. Okay, and the liquid down here. Okay, because the gas is traveling significantly faster than the liquid because of sleep. So because of sleep, we have a different way how they occupy, and we call actually, so we define holdup, liquid holdup, has the ratio between the area of the liquid divided by the area of the pipe, okay, with sleep. Please note that this is with sleep. And actually the real density of the mixture then will be the holdup of the liquid times the density of the liquid plus 1 minus the holdup of the liquid times the density of the gas. Okay? And these numbers, holdup of the liquid, might be very different than this lambda of the liquid. That's lambda of the liquid. Yeah? One example when it travels much quicker, the gas than the liquid, is when it's flowing upwards. Okay? In the flow upwards, it's like the gravity, the gravitational forces are pulling much harder the liquid down than the gas. Okay? So that causes a slip that the gas will go much quicker. And in that case, you will have that condition. But if you have downwards flow, let's say you are going on a pipeline down, okay, in that case gravity is going to help the fluid. So what's going to happen then? If we take our non-slip condition, so let's put some comment here. In upwards flow, okay, again in downwards flow, gravity helps in that case liquid down, thus in that case velocity of the gas is less than the velocity of the liquid. And then what we have is, if we see the cross section, we will have that liquid will be maybe down here and gas will be all of that. Okay, and you will have a different holdup. And the main issue with all of these models is to calculate that holdup, because with that holdup we can calculate the density, and with the density we can do many things. So on top of identifying the flow pattern, we want to have the slip, okay, we want to have the density, and they are actually equivalent. I'm not going to show you here, not to overload it with equations, but if you have the holdup, you can calculate the real velocities, right? Well, maybe let's do it here. So how do you calculate if you have the holdup? How do you calculate the real velocities? You have, it's the real velocity of the liquid is equal to the Q of the liquid divided by the area of the liquid, right? Yes, and the area of the liquid is the holdup times the area of the pipe, QL, right? And if you see, that part here is the superficial velocity of the liquid divided by the holdup of the liquid. Yes, so if you have holdup and you have the superficial velocity, you can calculate the real velocity of the liquid, and the real velocity of the gas is the same, but just 1 minus the holdup times area of the pipe, velocity of the gas. So they are equivalent. Slip, holdup, they all of them contain the same information. The thing is that you have some equations that relate each one of them, but remember, they usually am away. If I have no slip, I can assume homogeneous flow. I can use straight away that equation and that equation. Okay. If I have slip, then I have to use something more complicated. Okay, I have to calculate the holdup, and I and I have to use maybe a more, I have to compute, if I have sleep, if I look at the liquid phase, for example, separately, the liquid phase will have certain shear caused by the gas, okay, certain tau caused by the gas. And if I look at the gas, it will have certain shear caused by the liquid. Okay, and I have to include that shear, this tau, in the equation, the conservation equation. Because I have to apply one equation for this, that will be pressure acting here, the gravitational forces, the tau, okay? And then I have to apply the same equation, a similar equation for the gas. Pressure here, the gravitational, and the tau. And the tau, of course, the tau against the wall. Okay? So that's more or less, that's the basics of the... So now we reach the final point. If that's clear, that's what I expect you to know from multi-phase flow to understand our calculations. So how to perform multi-phase calculations in conduits. So we depart from a point with known pressure and temperature. Okay, and I usually, what I do, I assume the rate. Okay, I have the rate, assume the rate. So let's say we have a point here at the base of the tubing. We want to move up, so we have P1 and T1, and we have also a rate. And that rate, we need to have rate of oil, rate of gas, and rate of water, right, if there is any. But we need to have the three rates. Assume rate and calculate the rest with GOR or water cut, okay, if you have it. After I have that, that will be the first step. The second step will be to calculate from a point, so this will be from a certain depth. The second point will be to convert from standard conditions to local conditions. Okay, so how do we do that? We can do it two ways. We can use a compositional model, EOS, okay, that we say first what is the, we calculate, we have the composition is available, that means set I, that's what we use for composition, the mole fraction of every component, methane, ethane, propane, etc. C1, C2, C3, and we have set C1, set C2, set C3. Then after that we can calculate the mass fraction of oil and gas. Okay, that will be xg, that will be the mass of gas divided by total mass at that particular pressure and temperature. And after we have that, then we can calculate, and we will do that now just in one example if we have time. We calculate the mass of gas and the mass of liquid at pressure and temperature with the total mass. Okay, then after that we calculate QG and QO using the properties that we calculated with our equation of state. Properties using basically density of the gas, density of the oil. I run out of space, and then we say After I have Q, I need the velocity, okay? Then I need finally end up with the velocity of the liquid and the velocity of the gas. Yeah? That clear? So what do we need? Composition, an equation of state. That might be Peng-Robinson or Redlich-Kwong, Suave. Then we calculate the mass fraction at that particular pressure and temperature. Then with the mass fraction and the total mass flow, we calculate mass flow of gas, mass flow of liquid. Then with the densities, we calculate the local volume rates. With the local volume rates, we calculate the velocity. Yeah? If there is another approach that is black oil, okay, we need to compute black oil properties. Okay, and these are usually from table or correlation. And we go is a bit more straightforward, but the thing is that I have to have my black oil properties. But it looks something like that. Just I do a matrix. Okay, I calculate. So these are my rates, are standard conditions that I have. These are the rates that I want at local conditions, and then I need my BG, my RS, my BO at that particular pressure and temperature that I'm calculating. Okay, then I obtain QG, QO, QW, and then next is the same. Okay, I do the same to calculate the velocities of the liquid and the velocities of the gas. Sorry, that will be the superficial velocities, okay? Because the velocities, we don't have them, okay? Depend on the cross section of the air of the pipe cross section, okay? Those are the superficial velocities. Then we compute. So then with the input, okay, with input that usually typically is VSL, VSG. You also have the diameter of the pipe, the inclination of the pipe, the roughness of the pipe, then the properties rho L, rho G, rho L, BG, BL, interfacial tension of oil and gas. If you have water, you need also the interfacial tension of oil and water, interfacial tension of gas and water. What else? With all of that, okay, you go to your multiphase expert, that he has these maps, mechanistic model, correlation, etc. And you ask the multiphase expert, just like we have done to the solver, please, expert, give me delta P over delta L, the gradient at that particular position, okay? You obtain delta P and delta L. And now, how do I calculate the next point? Okay, I have the pressure drop in this point in the tubing. So how do I calculate the next pressure? If you remember, that's numerical integration. Okay, you can do that by different methods, okay, and you can do it explicit or implicit. And here you have Euler method. You have what is the thing you have corrector? It's called corrector predictor. Yeah. Runge-Kutta etc. Okay, but actually what we make is we try to solve this differential equation dp dl with starting point p equal to po and l equal to lo at l equal to lo. Okay, and for that, that is just a very fancy way to say that if we're going to use Euler's method, we are going just to say that P1 in the next time step is equal to PO plus delta L times dP dL at LO. Okay, at, or we can say, not at LO, but let's call it ZO. Okay, Z, and here we will call it Z. Okay, and that will be, we are in this point, ZO, and we are calculating Z1, and all the sets, they might be referred from the top, okay, through vertical depth. Yeah, and that's using, if you see that analytical equation dP over dz, you can have many methods to evaluate. That's actually, that's not exactly numerical integration, but that's called ordinary differential equation, right? Ordinary differential equation, or integration of numerical integration of ordinary differential equation. Yeah, we have one starting point, we have the expression of the derivative, and we have many methods to calculate it. One method that I told you, Euler's, very simple. We say we come from that point to calculate the next. I just multiply times the delta L between the 2 points times the gradient. Yeah. What do I do for the next point? Now I have 1. I want to calculate 2. The same thing, but what do I need? The temperature, right? Because I have the temperature here, 0, but I need the temperature 1. So I have to, so for the next point, temperature 1 has to be, so you have to have temperature 1 from someplace, okay? For the next point, one needs to have temperature 2 or temperature 1 beforehand. Okay, maybe you assume just a linear relationship. That's what we will do now in the exercise, 70 to, for example, 60 degrees. Okay, and you calculate the temperature of each point in the pipe. Another way that is more complicated is if you have, or if a temperature drop model is available. Okay, you have, for example, a function, temperature has a function of depth. Okay, you can use also that to, the thing is that you have to have at every point, you have to have the temperature, and repeat. That clear? So you see, it's a lot of work. I have to discretize, and the most important thing is that after I obtain a solution at the wellhead, okay, I obtain that pressure. For example, if I'm making it equal to the separator pressure, I have, if the pressure, they are not the same, I have to repeat again. Try with another rate, try with another rate, try with another rate. So it's a bunch of stepwise calculations for each equilibrium point. It's not like I can have explicitly, like I had just, I have P1 and calculate P2 just by clearing it from an equation. Okay, I have to perform, to calculate P2, I have to go step by step, calculate P2, oh, it's not the value that I want. I repeat, again, oh, it's not the value that I want, again, etc. Okay, until I find the right rate. So it's very, that's why I told you it's very expensive, very time consuming, and that's why we want to use tables. sometimes to do these calculations. So I think we can use now the last 10 minutes to start at least our exercise. Okay, and our exercise says that's the composition that we have, and we have the surface rates of oil and gas, and bottom hole pressure, reservoir temperature, internal diameter of the tubing, the true vertical depth. Okay, that's the set that I was showing before. The wellhead temperature is 60, so I can perform just a linear interpolation between them. Standard conditions soil density and standard conditions gas density. Okay, and if you see here, I'm doing exactly departing from that point, calculating the superficial velocities, and then I will calculate delta P, and then progress to the next point. Yeah. So let's. I don't think we'll have time to do all of it, but let's at least do the first part. And the first part is to first I need something to calculate the local rates, right? I need a fluid model. I need a fluid calculator. Okay, to calculate. So let's put here that's a class exercise actually. To calculate, if you remember this XO, okay, the mass flow, the mass fraction of oil divided by the total mass rate, and the properties, I need a fluid model, okay, a calculator. And I told you there are two ways: equation of state, compositional, or you can use black oil. We're going to use compositional. And actually, unfortunately, I'm not sure what's happening with the HYSYS license. HYSYS is a so if you use compositional, we can use HYSYS. Okay, how many of you are familiar with HYSYS? Not many. Two. Okay, it's a process simulator. But we can use it also, it will be like an overkill, but we can use it also to generate properties. There is one free version, or there is one alternative called DWSim, that is an open source process simulator. It's an engineer working for Petrobras in this Urucu field. I think he has, likes to work extra work during the weekends, and he has developed a very nice open source free software process simulator called DWSim. So you can download it from the web. But I'm going just here to open it very quickly. So I downloaded this package. Then I go inside. I'm going to create a new simulation. Okay, and then I say I have to set up some things first. Which components? So if someone can tell me what components do I have, I think I have nitrogen is the first one. Next one. Huh? CO2. Carbon dioxide. Okay, the next one, methane. Next one. I think that's on the website. Ethane, propane, butane. And we have isobutane. And we have also N-butane. Maybe they don't put the N-butane. The next one is, yeah, we are going to get that's 0 anyhow, so we are going to neglect that. Isopentane and pentane. Pentane, normal. Then we have hexane, and then heptane, octane, nonane, and decane. Okay, I added all my components. Now I want to say which equation I'm going to use for all of those components. So I will choose Penn-Robinson. You can use all kind of equation that you want, and I will use that. We won't talk about it. Those of you taking the course of Curtis might know what's that for. And the system of equation, I will use the one that has bar. Okay, bar and degrees Celsius. That's C5. Finish. Before I do anything else, I save it. You know, it's nice, it's free, but it's a bit unstable sometimes, so I just recommend to save all the time. Now I add this material stream that is like a small container. Okay, it's like I have just a container with some material on it inside. So let's say that container should be at the points that I have. Okay, the pressure and the temperature of the first point is 147 bar and 70 degrees Celsius. 147 bar, 70 Celsius. And if you see below here, I have the composition that I have to provide. It assigns some compositions, all of them equal by default, but that's not what I have. So here I will need your help, or yeah, it's in fraction, I think, or yeah, it's in fraction. So this will be, it will take me some time, 0.04. 001.
You can try to split screen.
Yep. Let's see. Let's see if I can paste it. I'm not sure. Before it was not working, but let's see if it. Did it work?
Yeah.
Okay, good. Okay, and still we have some imbalance. Okay, very small, so I will click here and normalize to take all of them. It will change them slightly, so the sum will give 1, but the change was not much, so it's maybe some component was missing from there. I don't know. Okay, so I have that part. Okay, and now I go to the properties. Okay, still hasn't changed it, so I have to click here, accept change. And now let's see. Okay, now you have the composition that I want. And as you see here, I don't care too much about all of that. Mass flow rate. Okay, so I can assign a flow rate that, for my case, it doesn't matter too much. Okay, mass flow, I will put just 1. But what I'm interested is in the fraction. What I told you, the liquid fraction and the vapor fraction. So where do I have the mass fraction? Do you see it someplace? Phase molar fraction. Okay, so that means that I have completely full is liquid. Okay, it means that at that pressure and temperature I'm in liquid. I don't trust too much, so I will try to how can I verify it? By using the phase diagram, right? If I manage to generate the phase diagram for that composition, I want to see if the point is inside or outside. So let's see that part. I think it's let's just show it here. Attach utility. Okay, you click on the small sun next to the name, phase envelope, and I want to calculate for that stream the phase envelope. I want the phase envelope to be pressure versus temperature. I think that's correct, right? Pressure versus temperature. And yeah, and I want everything to be custom for now. So let's click calculate. And I hope it doesn't crash. Okay, and actually it should be the opposite, I think. Pressure, temperature versus pressure. Yeah. Okay. So you got some small mistake, okay, some error there, but in general looks fine, and that's the operating point. So that means we are okay, it's fine, we should be in pure liquid. Okay, so that part don't pay too much attention. When you go, let me just, those of you taking the course with Curtis, I think I have some say technical difficulties. Print screen. Okay, so I have my bubble point line, my current point. My current point, if I'm outside, that means that that's liquid. My critical point, and you see next to the critical point is always very difficult to converge the solution. So all of these just neglected. That's an error of the software, and it should be kind of a smooth line passing through the critical point. But you know, we don't complain. We got it for free. It's a very nice tool. You can do many things with it. So just, but it looks nice, okay? And it's what we expected. So just before we leave, so how do we, so what we have to make here is calculate. So what I say here, I calculate the total mass rate, okay, of oil at surface conditions. So for that I take the density at surface conditions times the rate, okay, and here I have to make a transformation from, that one converts from kilogram day, right, and then I have to change from kilogram day to kilogram per second. So I have to divide by 1 day. It's
56,400.
yeah, but is it for times that or divide by that? Yes, yes, I think it's divide by that. Okay, so times 24 times 3 600, sorry, yes, 9.8 looks reasonable, the number. And then I have again the rate of gas times 1000. Remember here I have an e to the 3, okay, that times the density of the gas at standard conditions. Here nothing is happening. I'm multiplying rate at standard condition and density at standard condition, divided by 24 times 3600, 2.1. That tells me that the total mass rate that is circulating through the wellbore is 11.9. Yeah, and now I want to see at that particular pressure and temperature how much oil and how much water how much gas do I have. So for that I go to this tab, right, and I say you have all of it is, the mass fraction is 1. Okay, so all of that 11 you have it has oil. Okay, and then the rest is just that number minus this number. That means that you have no gas, single phase flow, right? So we stop here, and then we not next class but next week we will continue, and we will use our expert, okay, to, if you see there is another Excel sheet called Multiphase calculator, okay, where you substitute all the properties of the fluid, the conditions of liquid and gas, and then it will estimate for you what is the flow pattern and what is the delta P dx. You don't have to know, but you just have to know how to use this expert. But you don't have to know what is behind this expert. So just to summarize, so on Thursday we have the session here in P2. You're going to work with the software. You're going to make hope we will have time to make a class exercise. And for next week, we will continue with this exercise, very short, and then the next topic. Okay? Before we close, any question? No? Okay. Take care.